Okay, before we continue, let me just make an announcement. There will be, by the end of today, we will have Lab 1 and Lab 2. Lab 2 on Moodle. Lab 1 is already there, but I will give further instructions. You've got 2 weeks to hand in Lab 1. Then after 1 week, you hand in Lab 2, which means you've got 2 weeks to practice Lab 1 and within 3 weeks to practice Lab 2. So if somebody gives you for something to look at and submit after 3 weeks, and you tell them that you couldn't submit because the Wi-Fi or internet within 3 weeks, I don't take such excuses. You've got 3 weeks. It's going to be up, both of them, today, with tasks that you need to achieve. All the instructions, latest tomorrow morning, you've got that. So end of next week, Lab 1 should be coming in. End of the following week, Lab 2 should be coming in. So practice. I will put there the numbers of the demis who you can email and ask. Of course, you know my email, you can do that, but better start with the demis. That is 3 weeks. Somebody will not do that, then will come back and tell me that, oh, I was uploading and something happened. So that won't work. Okay, anybody with a question on that? If you have a comment, if you have a question, you can talk, raise your hand, or you can send me a chat. Okay, with that, let's continue with what we are doing on optimization. We will go through what we did yesterday. We're looking at state reduction. You can reduce the states of a finite state machine to make it cheaper and more optimal, but you are not supposed to change the behavior. You don't change the input-output relationship. So the motivation is to lower the cost by using fewer flip-flops, fewer gates, and it is because it is sometimes it's always good to design with more states and then you reduce later. So we started with the state reduction and we looked at row matching. We will go through it again. And next we will look at implication charts. There are so many methods, but we will only focus on these first two. So row matching, we said it's better to do it on a state table than a diagram. And then we produce the definition. This definition holds for whether you are looking at row matching, implication charts. You can only match, combine 1 or 2 states. It's not always 2. Could be 3, could be 4, if they are compatible. The name compatibility and equivalence are used interchangeably. For them to be compatible, to match, they must have the same output and transition to equivalent next states for the same input. We said equivalent next states could be same next state or to each other or self-loop for the same input. There is full compatibility and conditional or implied compatibility. Conditional implied means the outputs are okay. What is not right is just the next states. We will look at such things in details. So if states are compatible, you combine them into one and rename it. So you repeat until there is nothing to be combined. Row reduction is good for simple systems and is not guaranteed an optimal result. So we looked at that example. You've got a machine with 6 states. You need 3 flip-flops. Is there a way you can make that machine cheaper? So that is the state diagram. That is the state table. So we started here and asked ourselves, which states are compatible? Somebody can start with C and E. Another one can start with a different one. It doesn't matter. So Most people started with C and E, so we said C and E. Those ones who are not there, why are they compatible? You start with the output. For x equals to 0, it is 0, 0. That's fine. For x equals to 1, it is 1, 1. Both, not 1. If there is a mismatch here, don't waste time. They are not compatible. So that is first the first thing. Then you go for conditional compatibility of full. Here you've got FF, that's fine. AA, that's fine. So they are okay. So we replaced C and E with C. Wherever, removed the column E, wherever E is, we replaced with C. We merged them. So we got that. We've done away with E. Now we came here and said, between this, which one would you take? You can take different ones. Somebody can take B and F. Fine. Another one can take D and F. I took D and F because I just wanted to introduce another thing into each other. So you start with the output. 0, 0 is fine, 0, 0 is fine, CC is fine, and here they are looping into each other. That is a condition for equivalent next states, into each other or into themselves. So D and F, we merged and called it D. Wherever you see DE, here you replace. People forget and it causes problems. So we had that. Then we reached here, we checked, we said B and D can now be merged. 0, 0, 0, 0 here, you've got C here, then you've got D here. So you merge them, and then we had that. Then we said, what can you merge here? Look at the outputs. 1, 0 here, no. 1, 0 here, no. 0, 0 here, fine. 1, 0 here, no. So nothing can be merged further. So this is your final state diagram. The machine reduced from 6 to 3. From implementing with 3 flip-flops to implementing with 2. Thereby making your machine cheap. That we had done it. Okay, and then we went on the next one. A simple one is just to show you another different form of equivalence. You've got S0, S1, S2. Look at the outputs. The only ones which can be compatible is S0 and S2. This here, S1, S1, 5, S0 goes to S0, S2 goes to S2. They are self-looping. So we can combine them. And then we get that. After that, we can't do anything. So we've reduced it to 3, from 3 states to 2. 3 states you need 2 flip-flops, 2 states you need 1. So we've made our machine cheaper. I left you with that. You have these notes. So here is your machine, A, B, C, D, F. Of course, you have to get the state diagram. Okay, so quickly, which one was the first for you to combine? You can send me through the chat. You've done it. So let's just go through it quickly. Which one did you combine first? I'm waiting for an answer in the chat. You did this. Okay, yes. Okay, E and G. Abdul? E and G, E and G, you start from the output 1, 1, 0, 0, F, F, A, A, that is fine. So we've got E and G, and then you called it E, okay? So let's see. E and G, so we removed it and we had G is gone. The next, what did you combine? Okay, let's see the answers there. 7, you started with G and E. Okay, whichever you start, assuming we are here. So somebody in Jabulo says D and E. Okay, let's look at Jabulo. You are saying D and E. Let's look at D and E. It's good to make a mistake now. The outputs are okay. This is FF. This is E and A. So this is not compatible. This is conditional. If E and A. So in Jabulo, you can't do that here. E, you've got E and A here. That is not okay. So somebody says D and F. Sizwe, you say D and F. Let's look at your D and F. Okay, D and F, 1100 FF, E and E. That's fine. You can take those ones on. Let's see, D and F. So D and F gives you that. So here, what can you combine there? Okay, I'm opening the chart. Okay, you are saying C and A. It's good to try now and correct now. I like people who try. So, Steven, you are saying C and A. Let's look at C and A. The output 0000, the output is okay. But here you've got B and D. A and A is fine. But B and D you don't know. So you can't take that. That is conditional. It's conditioned on B and D. So that you can't take it. Any answer there? These two alone, you can't take them, yes? Okay, Nokolo, you say nothing. Sizwe, nothing. Okay. This one's 0101 DD file EA, you don't know. So here, this is conditional compatibility based on that. This one's here C and A, you don't know. Here A and C, you don't know. So I think nothing can be done from there. So your final machine is there. That is what we call row reduction method. Now, can you try it on that? I'm giving you 1 minute. You've been told minimize the circuit. I'm giving you 1 or 2 minutes. Tell me which ones will you combine, and then after that, what? Just try for me. 2 minutes. Okay, no call, no. Nabil, none. So you are supporting Yaya, no. Jabulo, nothing. Okay, I want you to check that. That's fine. So you see, row reduction is very basic. It works for very basic stuff. You might see and tell me that nothing is compatible here because row reduction is limited. But there are some conditional compatibilities which would be conditional and all that. So you need better methods to determine compatibility. Row reduction is very basic. Like you guys are saying, there's nothing compatible there. But let's see. There is another method. Okay, the other method is called implication charts. You have used row reduction, you've told me nothing is compatible. So now let's look at the same state diagram. We are going to use another method called the implication charts. And just participate. We'll go through it once and you won't have a problem. Okay, so which method is this? So, okay, now that is our table there. Draw a chart, not the arrangement here. Draw this chart because we are going to do this. Draw A, B, C, D, E, F, G. And then this one start from B, C, D, E, F, G, H. Draw it. I'm giving you time to draw it. Digital electronics is a very basic course. Whoever fails this does not participate. And on my side, you know how I set tests, you know what, copying is not easy. I know people are passing other courses, but mine from digital, my side, and what, doesn't matter whether you do it online with a friend there, doesn't matter. You just have to know what you are doing. So if you sit there, watch TV or do other things and think you will pass this course, not when I'm there. You just have to participate. If I say draw this, draw it. Let's do it, finish it and move on. And you also as your HOD, I need to warn you that you need to be careful. We've noted that and actually cracked down on lecturers who wrote questions, define. We know you've got books there. You will read it. We are clamping down on them. This semester is not going to be the same as last semester in other courses. There is the Bloom's taxonomy where they were setting questions at least, describe and what. That has stopped. Because we know you've got WhatsApp groups, you've got chats, you do with friends. We know that. So you have learned lessons. We have also learned lessons. So it's not going to be the same. Okay, just draw that. Once one of you finishes, just send me and say I've finished. Just draw the same chart. Forget about the X's. Just draw that A, B, C, D, E, F, G, B, C, D, E, F, G, H. Believe me, teachers an exam and the student messes in drawing these, they even get more confused. So if one of you has finished just drawing empty, tell me. Okay. Sahil, done. Sanelisiwe, done. Sizwe, done. Okay, now we are still using the same definition. Listen here, there are two things. There is one called conditional compatibility and incompatible. So we need to see that. Okay, Steven, fine. When the outputs don't match, it doesn't matter what the next state is. It doesn't matter what. It's incompatible. So let's look at A and B. Pay attention, A and B. You start with the outputs. 1, 0 is a mismatch. 0, 1 is a mismatch. They will never. There is nothing like condition. So in the square of A and B, they will never be compatible. They are incompatible. Put an X. And then do that. Check. If the outputs are okay, just leave it empty. Go to A and C. The outputs are okay. If the outputs are not okay, it's incompatible. Put an X. It will never. So do that for the rest. 2 minutes. Abdul. Okay, so what were we doing? What we were saying, we were looking here. We start with here. A, is A compatible with B? You come here, A and B. 1, 0, 0. Once you see this 1, 0, don't waste time. It will never. Put an X. So you got those X's. And where the outputs are okay, there is a possibility, conditional, you left them empty. Any question up to there? Now, you come, I will use this. We leave the X's. We come A and C. We are now coming to A and C. For A, remember this is A. It's got GB10A, GB10C, CF10, CF10. The outputs are okay. This is what you call conditional compatibility. Is if B is compatible to F and AND, that is an AND gate, and G is compatible to C, then A is compatible to what? C. I will repeat that. If B is compatible to F and G is compatible to C, then A is compatible to C. So put those conditions there. Fill it in. Okay, let me just go back here. Fill it in yourself. For A to be, the outputs are okay for A and C. 1, 0, 1, 1. We have dealt with this. There is no X. But for them to be compatible, B should be compatible to F, G should be compatible to C. So put CG here, FB or BF, it doesn't matter there. Those two must hold. So fill in that table. 2 minutes. The first person who fills in, just send me a chat. Then I'll wait for 2-3 more and we move. Just fill in the table. And believe me, once you do this, when the question comes like this, you know I've got my 10 marks. Okay, 2-3 minutes. Okay, then we will move on. Nobody's asking for more time. So let's see what you are saying there. What you are saying is you looked at A and C. For A to be compatible to C, C must be compatible to G, and B must be compatible to F. You can write F compatible to B. You can use a comma, whatever you mean. For A to be compatible to D, B must be compatible to E. For A to be compatible to G, D must be compatible to G, and B must be compatible to what? H. For B to be compatible to E, F must be compatible to H, and A must be compatible to G. For B to be compatible to F, for B to be compatible to F, C must be compatible to what? F. Let's stop there a moment. Give me your attention. For B to be compatible to F, C must be compatible to what? F. Now, the next step is to go through this. Let's look C and F. What are you saying here? That we come to C and F. You said no. That will never happen. So that cross that. Because you are saying for B to be compatible to F, C must be compatible to F. But in C and F, you say that will never happen. So this crosses out. Once you cross this out, you are saying B can never be compatible to F. Now you go through your table where there is B and F, like here, you said it won't, and cancel that. Go through the table and cancel until you are left with the compatible pairs. 2 minutes. If you want me to go through it, just ask again. Anybody wants me to go through it? You never shy. You are alone at home. Nobody's watching you. Just say, go through it again. Okay, I will repeat. You have filled in this. You filled in this. You've done this. That was the last step. I will start here. What does this mean? This means for A to be compatible to C, C must be compatible to G, and B must be compatible to F. This square means for A to be compatible to D, B must be compatible to E. That is the condition, conditional compatibility. The condition is this one. Where there is an X, you say A cannot be compatible to E. That is clear. The outputs don't agree. So let me skip to this. You know what that means. You know what that means. Let me skip up to here. You are saying for B to be compatible, B and F, that is a square for B compatible with what? F. For B to be compatible with F, C must be compatible with what? F. That is the condition. Let's look at C compatible with F. C and F, this square has an X. It means that will never happen. This C will never be compatible with F. For B to be compatible with F, C must be compatible with F, but this will never happen. So what does that tell you? There is an X here, because C will never be compatible with F. Once you put an X here, you are saying B will never be compatible with F. Now, if you go through the whole table, there is B and F here. I hope you are seeing my mouse. B and F is here. So for A to be compatible to C, we said C must be compatible to G and B must be compatible to F. And we've just seen that B can never be compatible to F. So that is also an X. And once you cancel that, it means wherever there is A and C, you have to check and cancel there. So can you go and put X's where the conditions cannot happen? 2 minutes until we will see what you are left with. Whenever you cancel out something, look where it affects. Is it a condition somewhere? If it is somewhere and you have cancelled it out, you have to cancel it there as well. So 2 minutes. The first ones just sent a chat. Okay, I'm taking questions. When you cross something, it means those two are not compatible. When you cross, they are not compatible. So if there are a condition somewhere, you keep on rechecking the whole table. When you cross something, you look, does it affect somewhere? You go there and cross there. If it's a condition somewhere, you go back and cross. So it's an iterative procedure. Once you cross something, you check, is it a condition anywhere in the table? If it is a condition and you crossed it, you cross where it is as well. So it's iterative until you are left with the last few. Okay, for the sake of time, we will move in. The rest of the people, I'm sure they've done it, but they are. So once you cancel something, you keep on canceling. Where any of the implied equivalents are false, cross out the box. Once you do that, once you cancel everything, you will be left with that. So that tells you E is compatible to H, D is compatible to G. So those are the only things that you are left with. So you used row reduction, you thought there was nothing compatible there, but implication charts has shown you that those two are compatible. Okay, now you can draw your reduced state table. We shouldn't waste time there. Okay, can you do that? 5 minutes. Now here you have to draw the table yourself and do it. Can you attempt that? Attempt this. Let's finish with this and go to some. The instructions are here. I'm giving you 5 minutes attempt, but when you finish that, please just send me a chat. I want to know. I always take the first 10 to 15 people to finish and assume is a true representation of the class. So can you please attempt that? Whenever they give you a reduction, don't use row reduction. It's very misleading unless you are told. Here we are looking at the implication table, so use the implication table. Go straight to the implication table. It does more than row reduction. Okay, we'll be forced to move on. Enough people have given me answers there, so I think we need to move on. Lectula, I've seen your answer. Okay, so those ones who did, you should have something like that. And based on that, anybody with a question here? You can correct yourself if you did something. So we had A, B, D, E, D, G, E, G. Now, we are going to the next level. If we are 3 people, this one is compatible, is a friend, A is a friend to B, B is a friend to C, C is a friend to A. It means we are all friends. We've been looking at only 2 pairs. But it doesn't. There could be more pairs that are compatible. For example, the right answer was A, B, D, E, D, G, E, G. So you can have A, B. These ones are compatible to each other. So D, E, G as one group. So you can reduce it actually to those 2 states. So we are going in an area where we will have multiple people being compatible. Okay. So if you have a question, you ask. So that was what. So implied table summary. The first step 1, construct a chart which contains a square for each pair of states. You have to know how it's arranged. Compare each pair of rows in output table. If the outputs associated, you start looking at the outputs and then place an X. If the outputs are not matching, you don't waste time. Trying to go back to where I was. Okay, that is where we were. We said you can have more states. Those are the things we need to look at. So we said this is a summary of how to work with an implied table. So the class exercise, when you go home, can you try and use an implied table to do that? These are the things that I said that once you have it, you need to know that if such a question comes, I've kept the marks in the pocket. So because of the disruption, next time we will start looking at but there isn't many people who have left anyway. And so I could just briefly look at this. The next one is incompletely specified states. You've not seen them when you are looking at asynchronous machines. But when you look at other machines, you will get them. So anyway, for the sake of the disruption and all that, I can see a lot of people have gone off. Let's start here next time. I will finish by saying your labs are going to be there online. It is basically simulation. You can use whatever software you want, but this Quarters Lite. You can get it from campus or you can download it. That is the best to use. So you'll have to simulate the labs. You'll have to design and simulate and show results. The results can be pictorial. For example, if it is a counter, you can show it through simulations, the counter counting and going through the sequence. When you say stop, it stops. We need the results, simulation results. So the labs will be there 2 and 3 weeks. So take your time, look at them. I don't want after 3 weeks you tell me I submit. Happens because you are seeing the deadline is 30 minutes from then. You've got 3 weeks. So they will be up. So just go through them and be okay. Otherwise, let's meet next time. Thanks.